In this video, we are going to learn how to perform automatic image registration. Specifically, we will talk about how to estimate geometric transform and how to specify image coordinates. This training will be useful for all AUVSI teams as it talks about the fundamental image processing and computer vision concept of image registration. We would also like to thank the Cedarville University RoboBoard team for providing us with image and video files for us to use in this training. For example, we are going to build a panoramic stitching algorithm. Let's take this example video here. Suppose you have a video like this that is approximately a panning shot. You would like to use this video and create a wide-angle image resulting in a panoramic scene like this. To do this, the basic operation is to know how to automatically register every frame in the video to its neighboring frame. Registration means comparing different images and bringing them into the same coordinate system. Consider two images, one of which is taken as a fixed image, the reference image with respect to which we are going to register, and the other one is the moving image that is going to be manipulated to register to the fixed image. In the example images here, the bigger green buoy has moved in the moving image. Now, the relationship between these two images is obtained by estimating a geometric transform between the two images. The first step to do this is feature matching. This has been discussed in the feature matching video. The result of this operation is a set of matched features and their respective locations in the two images. By feeding this information to the estimate geometric transform function, we can obtain the transformation matrix T-form, which defines the relationship between the two images. This transformation can then be applied to the moving image using the imwarp function to morph the moving image and register it to the fixed image. Here we see the transformed output image and the output image overlaid on top of the fixed image. If we took the green buoy for reference here, you can see how the moving image has been transformed to lay on top of the fixed image. Let's switch to MATLAB to see how this can be done. We begin with a feature matching between the two images. For this, we are going to evaluate the script we discussed in the feature matching video, matchFrames.m. To recap, we first load the frames of interest to us. Then we detect the features of each of the two frames. In this case, we use the MSER algorithm. Following this, we extract the feature sets for the two frames. We then match them, and then finally we visualize the matched features using the show matched features function. Let's go ahead and execute the script and take a look at the output. Here are the two matched features here. Let's go back to MATLAB here. At the end of this operation, we have two sets of points corresponding to the two images that are matched. These are the variables matched points 1 and matched points 2. To obtain the relationship between these 2 points, we can use the estimate geometric transform function. To do this, let's open up a starter MATLAB script called transformFrames_start. This starter script has several code sections and comments that will help us build our algorithm. First, we run the script for feature matching. Then, let's use the estimate geometric transform function. To do this, we can say estimate geometric transform of. We feed the matched points and the type of the transformation to estimate here. We will specify matched points 2, then matched points 1, so that we can find the transformation of the moving image with respect to the fixed image. If we specify matched points 1 first and then matched points 2, the function would estimate the transformation from the fixed image to the moving image instead. Next, our choice of transformation here depends on whether the images are transformed by rotation, scaling, or shearing. Apart from this, the transformation type also depends on the number of control pairs we provide. For example, a similarity transformation requires at least 2 control point pairs, and a projective requires at least 4. Please refer to the documentation of this function to get more information about the transform types and other optional parameters and understand how they apply to your particular application. We will use the projective transform type here. The output of this function is the estimated transform itself and the points that were used for estimation. So here we can say transformation T form, comma, inlier points 2, comma, inlier points 1. Note here that the estimate geometric transform function does not automatically use all the points fed into it for estimating the transform. It has an estimation algorithm that automatically removes the outliers in the supplied points. Let's go back to our matched features here. For example, the function will automatically remove the points matched in the water reflection here because it is an outlier. Let's go back to the script here. Because of the randomized nature of the algorithm, results may not be identical between runs. To assure that we are able to reproduce the behavior for consecutive runs, we will load a random number generator state saved in a mat file using the RNG command. So here we can say load random initializer .mat, which is the mat file that has my random state. And then we can use the RNG command to set the random number generator. So here we can set the state by providing the variable name. In this case, it is random state. We will also reset the random number generator to its default state after the estimate geometric transform here. So we can say RNG of default. Let's go ahead and run this section here. Go back to MATLAB and take a look at T-form. Here we see that the output T-form is of type projective 2D. This is because we set the transformation type of the estimate geometric transform function to projective. Depending on the transformation type, our output type will also vary. Here are the points that were used for estimation. We can visualize these points using the show matched features function that we discussed in the feature matching video. To do this, let's go back to the script here. So here, let's open up a new figure and then use the show matched features function. And then provide the images first. So in this case, I can say with frame 1, with frame 2, followed by the inlier points in this case. So here I can say inlier points 1, which corresponds to the first frame, then inlier points 2, which corresponds to the second frame, followed by the display method here. In this case, we will stick to montage to show the frames side by side. Let's go ahead and run this section also and take a look at the output. So here we can see the points that were used for estimating the geometric transform. We can also see that the points matched in the water reflection earlier has been removed. Now that the transform has been obtained, it can be applied to the moving frame using the imwarp function. To do this, let's go back to the script here. So here we can say moving 1 equals imwarp of the first argument for IMWarp is the image that needs to be transformed. So in this case, that is with frame 2, which is our moving image, followed by the transformation itself. So in this case, that is T-form. After this, we visualize our images. We already have code for this to visualize the fixed image, the moving image, the transformed moving image, and the transformed and fixed images overlaid on top of each other. So let's go back to our IMWarp function here. Let's go ahead and run this section here, and then visualize our images, and take a look at this output. Here we see the fixed image and the moving image. Note the green buoy here for reference. Note the transformed and overlaid images here. It looks like the transformation did not work entirely, since our transformed moving image is not looking similar to our fixed image. That is, for example, the big green buoy here should be near the center and the background tree line should somewhat line up. Our transformed image does not fit very well with the fixed image. This is because the two images have two different image coordinate systems that don't line up. To make them look similar, we need to make them have the same image coordinate system. Let's go back to the presentation to see what this means. For example, we have a fixed and a moving image here. To express the moving image in terms of the fixed image coordinate system, we can create an image coordinate reference system. We can do this using the imref2d function. In our case, since we would like to create a system similar to the fixed image, we can just provide the size of the fixed image to the imref2d function. The output of this can then be fed to the output view parameter in the imwarp function call to make the transformed image have the same system as the fixed image. Let's go back to MATLAB and see how we can do this. So here, we can create the fixed coordinate system. So we can say R fixed equals imref2d of. Here we can provide the size of the fixed image. So here we can say size of with frame 1, which is our fixed image. Then we feed this to the imwarp function to perform the transformation. So here we can say moving 2 equals imwarp of. First we provide the name of the frame that needs to be transformed. So in this case, that's with frame 2, followed by the transformation. So that is T-form. Now we can set the output view parameter. So here we can say output view, and then set it to R fixed, which is the coordinate system which we just created. Let's go ahead and run this section here, and then visualize our images, and take a look at our output here. Now we see that the images look like they lay on top of each other. The green buoy looks close to each other near the center, and the tree line also seems to line up better. We can imagine if we do this automatically in a loop for consecutive frames in a video, we can stitch a panoramic image. To do this, let's go back to MATLAB here and open up a starter script called stitch panorama_start. This starter script also has several code sections and comments that will help us build our algorithm. We begin with a video file reader to bring video frames consecutively into MATLAB. Since we are going to be performing feature matching with the video frames, we are interested in grayscale, hence we request the output color space to be intensity. Next, we initialize the features of the first frame using detect and extract features functions. Then we will implement the loop where we are going to consecutively take the video frames, detect, extract, and match features with the neighboring video frames, and then finally estimate the geometric transform between the consecutive frames. This is similar to the transformation example we just went through. First, we will assign the points and the features of the previous frame, which for the first iteration will be the first frame. So here we can say points previous equals points, features previous equals features. Notice that points and features here have been computed in this section here. Let's go back to our code here. Then we need to detect, extract, and match features with the next frame. First, to detect features, let's go back up. Copy the code here, which is used to bring in our video frame and then detect our features, and then paste it here. Then, to extract features, we will copy the final line in this section here, and then paste it here. Next, we need to match features. To do this, we will use the match features function. Recall that match features returns the index of the features of the corresponding frames that are matched. So here we can say index pairs equals match features of our two feature sets, in this case that is features and then features previous. Then, similar to our feature matching video, we can obtain the matched points by indexing into the points variable. So here I can say matched points equals all the points returned by the feature extraction, and narrow it down using our index pairs variable, and in this case only the first column of the index pairs variable. Similarly, we will obtain the matched points for our previous frame. To do this, we will just copy this code here, paste it here, and then we can say matched points previous equals points previous of index pairs, but in this case the second column here. Using the matched points of these two frames, we can estimate the transform and store it in a matrix. So here we can say T-forms of index equals estimate geometric transform of matched points, comma, matched points previous, followed by the transformation type. We will stick to using projective similar to our transformation example. T-form for every index will provide the transformation between neighboring frames. To keep track of the overall transform for that frame with respect to the first frame, we would need to multiply the transformation here. So here we can say T-forms of index dot T, which is where the value of the transformation matrix lies, equals T-forms of index minus 1 dot T multiplied by T-forms of index dot T. Let's go ahead and save this file here as stitch panorama underscore scene. Let's go ahead and close all our figures and clear our workspace and run this here. Go back to MATLAB. Let's scroll down here to find T-forms. So here we see T-forms has 39 elements, which means our video has 39 frames. The next task is to find the output panorama image size so that we can initialize it appropriately. For this, we would need the minimum and maximum widths and heights of the transformed image. Let's go back to our script here. Let's first compute the size of our image. So we can say image size equals size of gray image, which is the name of our frame. Let's denote the limits across the width of the image using xmin and xmax. We will initialize the minimum values to be at 1 pixel and the maximum value to the width and the height of the image respectively for our limits. So here we can say x min equals 1, x max equals image size. The second element is the width of the image. Then y min equals 1, y max equals image size of 1, which is the height of the image. Followed by this, we need to figure out what are the output limits for each image corresponding to every transformation matrix. To do this, let's start a loop here for index equals 1 colon the number of elements in the transformation array. So here we can say x limit comma y limit equals, given the transformation and the input image size as inputs, the output limit function can find the output image size. So here we can say output limits of, provide the transformation matrix first. So in this case, that is t forms of index, followed by the x and y limits of the input image. So in this case, we can provide that as an array of 1 and image size of 2. This is across the width of the input image, and 1 and image size of 1, and this is across the height of the input image. The output x limit and y limit are also arrays where the first element corresponds to the minimum limit and the second element corresponds to the maximum limit. So to compute our x min and x max here, we can say x min equals minimum of x min comma x limit, take the first element here, and then we can compute x max equals max of x max comma x limit of element 2. This is for the width of the image. For the height of the image, let's go ahead and copy these two commands and then paste them using Ctrl C and Ctrl V. And here we can edit this to y min and y limits and y max and y limit again. Let's go ahead and end this loop here. Now we can use the min and max values here to find the overall width and height of the panorama image. So here we can say width equals x max minus x min, and height equals y max minus y min. Let's also use round to round these values to the nearest pixel value instead of decimals. Next, for the panoramic registration to be successful, the output image needs to be in the same coordinate system as the panoramic canvas. We are going to create a panoramic image coordinate system so that all our output images will be in that system. So here we can say x limits equals x min, x max, y limits equals y min, y max. These two arrays hold the overall x and y limits for the panoramic image. Now to create the coordinate system, we can say panorama view equals, use the imref2d function similar to our transformation example, provide the size of the panoramic image, so in this case that is height and width variables, followed by the x and y limits of the image. So in this case, it's the variables that we just created. So we can say x limits, comma, y limits here. Finally, we are going to create the panoramic image. We can use the zeros function to initialize the image of appropriate size and data type. All of our frames from the video file reader system object are of default single data type, so we will also initialize the panorama to the same type. So here we can say panorama equals zeros of the size of the image. So in this case, that is height and width, followed by the data type. So in this case, that is single. Before we implement the loop for the panoramic image registration, let's go ahead and reset our video file reader. So here we can say reset of vid reader. Let's reinitialize our loop variable. So in this case, index equals 1. Then begin our loop here. So in this case, we can say while our video file reader is not done. So let's use the not operator here. And then inside the loop, let's go ahead and read in our image. So in this case, gray image equals step of our video reader. Then we use the imwarp function with the estimated transform and the output image coordinate system. So in this case, we can say warped image equals imwarp of the image that needs to be warped. So in this case, that is gray image, followed by the transform. So in this case, that is tforms. And then let's set the output view parameter. So in this case, output view can be set to our variable panorama view. Let's go ahead and set our panorama variable to our warped image here. And then use imshow here to visualize our panorama. So here we can say imshow of panorama. Let's also increment our loop variable here. So index equals index plus 1 and end our loop. Notice that we are using a couple of system objects here. So let's also make sure we clean up the system objects by releasing them. Let's go ahead and save our script, close all our figures and clear our workspace, and run the script here to see what the output looks like. The output seems like a sliding window. This is because all the pixels are overwritten with the newly transformed image every iteration. Instead, we need to provide specifically which pixels to overwrite. To do this, we can use the alpha blender system object. This system object helps us combine and overlay images. Let's go back to our script here. Go back up here. So here, let's create our alpha blender system object. So in this case, h blender equals vision dot alpha blender. To provide specific pixels, we can use the alpha blender in the binary mask operation mode. So here we can set the operation property to binary mask and set the mask source to the input port, which means we can specify this when we call the step on the system object. Let's go back to the loop here. Since the alpha blender is now expecting a binary mask through the input port, we need to first calculate the mask inside this loop. The mask is a binary image that specifies the location of the non-zero pixels in the image that we need to overwrite. We can do this by saying warped mask equals warped image greater than 0. This way, warped mask contains the information of all the non-zero pixels in warped image. Now to create the panorama image, in this case, we will use the step on our alpha blender system object and then provide the images that need to be blended. So in this case, that's the panoramic canvas followed by the warped image, and also provide the mask for the specific pixels to overwrite. So in this case, that is warped mask. Let's go ahead and save this file. Close all our figures and clear our workspace and run the script here. Now we see that the images are retained from the previous iterations. Several image processing operations can be done to make this algorithm better. Refer to the example and exercise files to see how to remove the edge artifacts and how to center a panorama on a particular image like some of the mobile cameras do. However, remember that the crux of this algorithm is still feature matching and automatic registration. Let's go back to the presentation and do a recap. We talked about creating a panoramic scene. The algorithm consisted of detecting common features and then registering consecutive frames of the video based on the features to get a panoramic scene. Specifically, these were all the tasks that were performed for panoramic stitching. We used video file reader to read in the video frames. We performed feature matching using the various functions we discussed in the feature matching video. We estimated the transform between the two consecutive frames with their feature sets using estimate geometric transform. We then calculated the panoramic image size using the output limits function. Finally, using imwarp and imref2d, we transformed every frame and overlaid it in a canvas using the alpha blender system object. In summary, we talked about how to estimate geometric transform in conjunction with feature matching and how to specify image coordinates. This concludes this video.